tumble and do all sorts of intricate dance are pretty common. So magnetic skyrmions, and you can see Lorentz microscopy imaging of magnetic skyrmions, and largely that is because you can twist and turn spins, because spin lattice coupling is typically weak. So you don't have so much strain penalty in trying to tumble and twist and make all kinds of intricate structures with spins. Whereas on the other hand, the ferroelectrics and polarization that we're going to talk about today are like the Stonehenge in Salisbury Plains in UK. These are 3,000-year-old structures, 3,000 BC, so they are really 5,000-year-old structures. The electric polarizations, you like to either point up, point down. If you try to do other things, like in the background here, if you don't want any gaps, like the gaps left here, you'd have to create domain walls, and those cost energy. So the whole premise of today's talk is, can we take electric polarization and try to turn it into a putty dough and twist and turn them like spins, like we can do with spins. It turns out that the polarization in ferroelectrics do twist and tumble a little bit. So if this were the Stonehenge, they really like to stand up or down. If you try to do anything else, they'd go to zero, they'd disappear on you. Those are the classic Ising type walls. Whereas if they twist across a domain wall, they're twisting across, that's a block wall. If they tumble across, that's a nail wall. You can have some mixed combinations of these as well. It turns out that in 2009, we published a paper with theory collaborators, Chen, Susan Sinnott, Simon Philpott, that classic ferroelectrics like lithium niobate and barium and lead titanate, they do have a bit of twist and tumble. So the black line here is the Ising type wall, the Stonehenge we are talking about, and these are the twists and tumbles, right, very close to a few unit cells around the wall. But it's a very slight amount. They do that, and then they disappear and then show up on the other side. So the question is, can we make them do a lot more? Can they twist and tumble a lot more? And in order to answer that question, we should really answer a different question. Oops. Let's see. Sorry about that. So we should try to answer a different question. And the different question is, why do crystals even form? And so here is rock salt, and you can see sodium chloride. Every sodium is surrounded by 6 chlorines and so on and so forth. And the answer is, most of the energy gain that comes, it's a very hand-waving argument. It comes from largely local neighbors, minimizing the interactions with local neighbors. And if you like your neighbors, you don't really want to move neighborhood, right? So you just stick with it and you keep repeating it, you form a crystal. So if you really want atoms, and in our case dipoles, to have long range interactions and care about very long range structures, neighbors far away, then the secret is to frustrate local interactions. And the way, indeed it works out. So in this paper, we showed that with 4 layers of strontium titanate and 8 layers of barium titanate, and repeating this in the Z direction, you do get vortices, and you get tumbling in this direction, you get twists in this direction, as they're shown over here. So you can get these sorts of things. We even tried to make them and look for them. In those days, electron microscopy was not what it is today. And barium titanate doesn't have a very big C to A ratio. It was hard to detect them. But we were not really the only people in the game. In fact, the very first report of such twisting and tumbling was from Belaish and Fu in 2004. And in 2012, Aguado, Puente, Junquera, they predicted lead titanate, strontium titanate system with vortices, polar vortices forming in the lead titanate layer. In 2016, Ramesh's group and Lane Martin's group in Berkeley, they actually realized this. This is lead titanate. This is strontium titanate. It's grown with exquisite control over interfaces and the number of layers. And this is electron microscopy. The yellow arrows show you that the ferroelectric polarization, which is titanium displacing from its octahedral center, is showing right-handed and left-handed curling. And this goes on and repeats. And the question is, why did this happen? So if you think a little bit about it, well, where is this frustration? Why are they caring about long-range interactions across and through this layer? And there are really two types of clever frustrations that are built into the structure. One is that lead titanate is actually under compression, the way it is grown on the substrate, the scandate substrate. If it's under compression, it wants to press in, and the polarization really wants to stand up. The arrows, the stone hinges want to be up or down. Okay. Strontium titanate, on the other hand, is under tension, and it is shown that when you pull this, it does lie down, and the polarization goes flat. It's much smaller than this. So there is this tension, compression, that sort of a frustration is built in. The other order parameter that's varying is this is ferroelectric, this is not, this is ferroelectric and not. So there is strong divergence of polarization at this interface. In other words, if you run straight into this interface, you're going to have a lot of bound charges building up at these two interfaces. That's not very good. It costs energy. So as these things, but because they are under compression, they want to stand up. So as they approach the interface, they turn over either to the left or to the right, and they start making these swirls. And that's what leads to these ferroelectric vortices. Okay, so these two types of long-range frustrations are leading to long-range structures. So if you vary the number of these two layers, lead titanate to strontium titanate, at very long and very short, you get regular domains, but some intermediate state, you get these swirls. And here is a phase field simulation of that sort of swirl from Longking Chen's group. And you can see that these swirls are forming in each of these layers. And you can see that video is started over again. You can start seeing in a few seconds these swirls starting to form. And that's what we see saw in the previous electron microscope picture. All right, so not only swirls, but the other things have been shown. If you change the substrate, go towards strontium titanate, you see bubbles. This was again predicted by Chen's group, and it was confirmed by Ramesh and Martin's group at Berkeley. And here is a phase field simulation of one of these bubbles. You can see it's really, the polarization can be twisted and turned like a putty dough, and not, it's behaving very differently from a Stonehenge now. So that is the beauty of it. So you want to build in frustrations. Okay, so that is the starting point for some of the stuff that I'm going to talk about today, which is all about non-equilibrium landscape. So we're starting with one of these films from Ramesh and Lane's group, where you have these polar vortices inside the lead titanate layer, and some of this coexists with regular ferroelectric domains. This is called A1, A2, A1, A2. It's also called step ladder type domains. So there's a mishmash of these vortices and regular ferroelectric domains. And what we are going to do is, and this is Vlad Stoica, who did this work initially. A lot of the credit for what I'm going to show you goes to him and the team that has supported all of this work. So we hit this with an ultra-fast laser pulse. Okay, And so that's the experiment where you come in with light at 400 nanometer. It's slightly absorbed by lead titanate. So that's very important. It should be absorbed by one of the layers here to generate carriers. It has to be short enough, and I'll talk about that later. It has to have enough fluence to generate enough carriers. And while at the same time, we are looking with X-ray and looking at what is happening to the structure. And this is one of these superlattices with a mishmash of vortices and ferroelectric domains. And something remarkable happened here. So what happens is you start with this mishmash. These are X-ray strain diagrams. You can do X-ray microscopy, done at Argonne National Lab, and some of the image processing at Oak Ridge. And you can see the vortices are blues, and the regular ferroelectric domains are called A here. And they are in the maroon color. And it's a mishmash. You hit it with light, and the strain is almost gone. It's almost zero. There's still some very little bit structure left. This whole thing turns out to be a single phase, okay? And the question is, what happened? What did we do? What kind of changes have happened? Why have they happened, and how? And that is the story that I'm going to talk about in the rest of the slides today, okay? All right, so we, as all things in condensed matter, we love the reciprocal space. That's the energy and momentum space. I also call it upside down space and time. So this was before, and this is this is the vertical direction. The periodic layers are in this direction if this was real space. And the lead titanate, strontium titanate layers are this way. And this is before, and this is after. An after phase we are going to call a supercrystal phase. And you can see just even visually that there are a lot of satellite peaks, many, many peaks that are showing up. It's just absolutely gorgeous. Something dramatic has happened here. And not only do we take one cut in the reciprocal space, you cut in many different directions, and we reconstruct this. And we'll see this is a huge single crystal that we have created, huge unit cell. And so we need a lot of cuts and a lot of reciprocal space to reconstruct what happened. And so that's what we'll do in the next few slides. I'll walk you through some of these cuts. So think about in KL cut. And if you think about the vortices, the L is the reciprocal direction, but it's basically in real space perpendicular to the layers. And K is along these polar vortices, these let's just call them spring rolls. They're along those spring rolls. And you can sort of see little splittings here. The vortex, and the A is the regular ferroelectric vortex phase, the ferroelectric phase, vortex phase, ferroelectric phase. And this is one, so 0 is 0th order, 1 is the first order, this is minus first order. And because it's a periodic lattice, you get different orders in the Z direction. That is really from construction, 16 unit cells of lead titanate, 16 unit cells of strontium titanate, and you're repeating this. This is coming from that. All right, so this is before, and when you hit it, you get that. Okay? And we're talking about reciprocal space with in that cut, K and L. Okay, and there is a lot going on. So let me just break it down a little bit. If you look at this spacing, this is about 12.55 nanometers in real space, if you convert it to real space. And that is basically the periodicity of the grown structure. This is a superlattice. It was grown that way. Very good. We didn't have anything to do with it. But once you hit it with this laser pulse, you see that there is another periodicity. This is around double this that is showing up in the Z direction. Okay, so there is another periodicity showing up here. It's almost as though every lead titanate layer is now different. So it's lead titanate, strontium titanate, and lead titanate, strontium titanate. The next lead titanate is different. So there's a dark blue and a light blue lead titanate. At least that's what this is indicating. And in the other direction, along this direction, there were no periodicities in this direction before, but now you see, you can see there were no periodicities this way, but now you have almost 30 nanometer periodicity along the tubes. So there's some new type of crystalline order that has emerged with very long periodicities of 30 nanometers. Okay. Let's look at this cut. L is still the same. H is now perpendicular to these vortices. Again, you have the same sort of superlattice, and you have 11 nanometers. You see there is a periodicity here of 11 nanometers, and that's simply due to these vortices. This is spacing, the 11 nanometers shown here, spacing from one left-handed to another left-handed vortex. Okay. Now, after light hits this the structure, you get again a doubling in the z direction, just like before. But not only do you have the 11 nanometer, you have another one, 27.5 nanometer. So even in this direction, there is another periodicity that's emerging. And I have something more to say about this in a second. So I'm jumping a little bit, but the phase field modeling, once we compared it, showed this is a real space image of just the lead titanate layer. What we are forming are vortices and anti-vortices. So that's half of 11 nanometer. And then in the other direction, there are also new vortices that are now emerging, vortices and anti-vortices. This is half of 27.5 nanometers. So this is the other periodicity that we were seeing. So now you literally have some sort of a DNA type origami, except this is it with inorganic crystals. You have vortices or polar vortices in one direction interweaving with polar vortices in the vertical direction, forming some very complex structure. And some of these periodicities are coming from there. So if you finally look at this in plane direction, this is the HK plane, you can sort of get an aerial view of all these periods we've already seen, about 30 nanometers this way. And there were two different along these tubes, or perpendicular to these tubes. You had 11 nanometer because of this, and then there is another 27.5 nanometer. Now these even new periodicities interact and give you peaks like E. Okay? If you take one of these peaks and you do imaging, what you find is there is a single phase. It's a huge unit cell. And there are really two phases. One is a majority phase, almost 90%. We call it a 3D supercrystal. And then there is a little bit, 10% of minority phase, which has also got this extra periodicity. See, there is within one direction, there are two different periods. So we call that 4D. But that 4D thing really exists only in a minor phase. Most of it is 3D. And I'm really going to focus on this 3D phase today. All right, the films are also commensurate with the substrate. So how does that match up? It's quite remarkable what happens. So this is an off-specular peak before and after. So the ferroelectric, so the substrate is somewhere over here, right? This dotted white line. The ferroelectric is a little bit to the left. The vortex is a little bit to the right. So we had a mishmash before. And after you hit it, you get the supercrystal is right smack on. It's nicely commensurate with the substrate. So it automatically finds this perfect matching so that the in plane is commensurate with the substrate. The in plane strain of the supercrystal is commensurate with the substrate. You can see that also in the peaks. You have vortex, and let's say pick any given order, like let's say -4. Vortex and A1, A2, this was the mishmash. And both of them disappear when you hit with light. And in between those two, you get a supercrystal phase with the same -4 order. And the interesting thing is This is not a transient phase. Once you hit it with laser light, this is created, it sticks around forever. We can look at it after 6 months, it's still there. And you have to heat it. You have to heat it to almost 450, 500 Kelvin. And then you see that this is gone back to the original state. You can't get back the supercrystal, just by heating and cooling. You really need this laser pulse. It needs to have certain characteristics. And that's really the mystery. So where did this come from and how are we able to create this? Okay. So this is really the full glory of the entire crystal. And this is a phase field simulation of what was reconstructed. So the unit cell, just to again reiterate, almost 30 nanometer in one direction. There are two different periodicities in the other direction, at least in 10% of the crystal. In almost 90%, there's one of these. And in the third direction, this is really another periodicity that emerges beyond the growth of lead titanate and strontium titanate. Right? So we have this incredible huge unit cell showing up from nowhere. It's metastable, and it's really, it'll stick around until you heat it, like I said, to 450 Kelvin. Now we want to understand this, so that we have spent a lot of time since in the past few years to try to understand this. The very first attempt in the original paper was a square cow model. So we know we are coming in with light, we are exciting charges, there is some temperature change, there is some strain change. We didn't want to deal with all of that. All we did was we said, well, if there are charges being pumped, maybe the dielectric constant increases. We simply took the background dielectric constant, made it a variable. Little simple, in fact, a single parameter, variable parameter experiment, numerical experiment. And lo and behold, we saw a supercrystal emerging in this phase field. If we start from this sort of mishmash phase, you can see that as you change, this order parameter is same equivalent of changing this dielectric constant, that as you change the dielectric constant, the electrical and gradient energy, there are more and more domain walls and more charging happening as the polarization twists and tumbles, goes up. The Landau and elastic energy go down, and the sum total has really a barrier. But then if you cross the barrier, it finds this new supercrystal state, and that shows up. So it's quite, we got quite lucky in some sense that we hit upon the right parameter, and right away we found the crystal that we were seeing experimentally. Maybe some of the details were missing and we didn't really understand the mechanism, but it was a good first start. Okay. This is some more of that square cow model. You increase the background dielectric constant. There is a certain threshold. It doesn't happen until you hit a certain threshold. We'll later see that you have to build up a certain amount of charge, and you need to have a certain temperature, when this kicks over. But then it switches over to the supercrystal phase. And when you come back, the supercrystal phase actually sort of is metastable. It may be a little bit disordered, but even if you reduce the dielectric constant back, you can get a disordered metastable supercrystal phase in the simulation. Okay. The other thing was to just check that indeed the simulation is what we think it is. Here is experiment. It's one of the zoomed in cuts of the KL cuts. Here is the phase field, just a Fourier transform of the phase field modeling. You can see it's pretty good. Here is another cut. The white dots here match the white dots here from phase field. But you'll see, there are these other black dots they are missing here. So clearly our square cow model here is not good enough. And we need to also, we don't really know what the mechanism was. So we need to do better. But it's worth seeing what has happened. So again, with the same square cow model, you see that if you look in, you see in the third direction along which the vortices were, now suddenly there is the A and C and A and C, there's this periodicity. And these guys are locking up some charges. It's almost like a battery. It's like a giant capacitor. And you can see the charge is quite significant. And if we calculate how much these charges are, add them up per unit volume, and we compute based on the number of photons we have in the absorption of lead titanate, how many carriers they should have, the two kind of match up. They are the same order of magnitude. So literally, we are exciting carriers, and the system is finding this ground state and locking up all of those charges by reconfiguring the polarization and creating what we can clearly call a charge-ordered state. Right? And it's also a strain-ordered state. You have positive and negative strains in this case in the epsilon kk direction, in plane direction. You can see that there are also strain dipoles inside this crystal. So you created a charge ordered and strain ordered supercrystal phase with tens of nanometers of unit cell size. Here's the temperature effect I was talking about. So if you look at the supercrystal and vortex peaks and you just watch them around 450 Kelvin, they are erased, they're gone. So until then, they're pretty stable. They'll stick around, like I said, but once you heat it to about 450 K, about 150 C or so, they're gone. And then if you come back, the supercrystal will not come back. You have to hit it again with light to create this. Now, the interesting thing is these stars indicate the charge that was locked up in the previous image, and that ordered charge ordering. And if you notice, that charge ordering is also gone. All that charge is released when you heat, and the supercrystal is gone. Okay? Melting of the charge order has taken place. A few other important details, which will give us the clue and the motivation for tracking this process in real time. So a lot of the work from here on that I'm going to talk about is not yet published, and some of it is brand new. So you'll be probably the first audience to be hearing about it. One of the things we found was that it mattered how much the laser fluence was, how much energy per unit area coming in. So this data was for, every point you had 100 shots, and then we looked whether something happened or not. You can see that nothing happens, nothing happens, nothing happens. At some threshold, boom, the supercrystal starts forming. The ferroelectric phase is going away. The vortex phase is again forming. You'll see that initially it's erased and then it reforms. Okay, so there is a threshold. You need to come in. There are really two things. One is you need to have the right color. You need to have the color of light that's above the band gap of lead titanate, so that the carriers are formed. If you come in with below the band gap, nothing is going to happen. You're not going to form supercrystal, and we have done this experiment. The other thing is you need to have enough fluence, and there is a threshold. If you come in with enough fluence, even more than 25 millijoules, you can even do this with a single laser shot. So here is mixed phase. With a single laser shot, it turns into this supercrystal phase. One single supercrystal phase. One laser shot, the whole thing is done, right? Around 40 millijoule or above 40 millijoule. You get this giant supercrystal. Okay? And the third thing, as I'll tell you, is the laser pulses have to be short. Okay, so if you come in with enough fluence and you look at with different fluences, how wide can the pulse be, for you to get the supercrystal? You find that the wider and wider you make the pulse, the more and more the threshold is for triggering the creation of the supercrystal. Here is another way to look at it. If you split up a laser pulse into two pulses and make the first one, sub-threshold, not enough to make the supercrystal, and come in with a delay with the second pulse and see if the two of them together would make a supercrystal, and watch how much delay is allowed, you'll find that you can't allow more than 10, 15 picosecond of delay. After that, it doesn't matter. You won't make a supercrystal. So the big picture or the takeaway here is that there is a threshold, And the pulses also have to be short, femtosecond to picosecond. And otherwise, you're not going to form this. Okay? So the question is, why is all this happening? I'll give you some clues, and then I'll point to some more recent experiments that tell you what is happening as soon as the laser hits. Okay? So the first thing is that that jolt of light, or literally a bolt of light is like a jolt of charge, right? So this is transient absorption. In other words, you're coming in with light and you're detecting the absorption of another laser beam. So it's called a pump probe transient absorption measurement. So you're seeing various colors. So in this case, this is the light that is coming in with different delays with various colors. And how much is it absorbed? The bigger the transient absorption, the more the carriers. You can see the carriers take off, and within a picosecond or two, it is thermalized with lattice. So with the phonons, right? So you have this window where if you inject charge, you have a few picoseconds before it thermalizes. So this jolt really needs to have enough charges to trigger that supercrystal formation. So this time scale becomes very important, this electron phonon thermalization time constant of a few picoseconds. Okay. And at about 10 picoseconds, it's all done, right? Okay. So that's a 1 to 10 picosecond, that number comes in here. If you just see the same thing with color of this light being absorbed versus transient absorption at different delays, you'll see that right after exciting, there is strong absorption very close to the offset. These are valence band and conduction band offset between lead titanate and strontium titanate. These are guesses from this paper. We don't have the exact numbers. And you can see that very quickly, there's very strong absorption close to these interfaces, the conduction valence band offsets. And as time goes by, it sort of settles down. Okay, the charges settle down. And there is some amount of charge that makes it to the interface, and that's what is going to trigger the nucleation of the supercrystal. But you need to pump enough so that enough of them make it to the interface. Okay? So what we learned so far is that very small time scale is important, and you need to pump enough charges. All right, so in order to study structurally what is happening, we needed single shot dynamics. So we had to go to SOCLA in Japan, and LCLS was very kind enough to give us sufficient beam times. And so we are coming in literally with one pulse of X-ray, and boom, the supercrystal is done. Okay. And then if you want to study again with another time delay or something, you have to move over and do another spot and another spot and another. So you need to do hundreds, thousands of spots on the sample for each experiment. So it's a little painful, but it's all beautifully done, computer controlled and everything. And we have, as I'll show you, we have done this experiment. So essentially, a whole series of laser pulses are coming, and the optical pulse comes in. The optical pulse at 400 nanometer comes in at some point, and we are varying this delay. And we are watching with X-ray what happened after that. So by varying the delay, a little bit after when the optical pulse arrived, what happens. Okay? And this is what happens. So these are detector images. So this axis is not nice L and some reciprocal direction. It's you're moving in two different directions here. Just some quirks of the measurement. These are vortex peaks, the original. This is minus 0.2 picosecond, meaning before the light arrived. And these are ferroelectric peaks. And after the light arrives, you see the vortex is almost gone. The ferroelectric is 0.6 picosecond by 20 picosecond. This ferroelectric domains are totally gone. The vortex domains are barely there. A little bit is there. So the very first thing is the collapse. So as soon as the light comes in, within order of picoseconds, both the initial phase of the vortex and the ferroelectric phases are nuked out. So here is another way of looking at the same thing with time. You see the ferroelectric phase and the vortex phase, boom, they're gone. These are some coherent fringes. It's not a Bragg peak. Um, so basically, you start with a clean slate right away, and you need that punch with enough charges and enough, as I'll point out, temperature to nuke the initial phases. So here is the big picture. When you do these kinds of experiments, here is the collapse I just talked about. Very quickly, the vortex in black and the ferroelectric in red, boom, all of this is wiped out within a few picoseconds. And then nothing happens. I mean, something is happening, but it just looks from X-ray like nothing is happening, nothing is happening. And then you switch over, now you are in nanoseconds and nothing is happening. And around 10 nanoseconds, there is some stirring in the supercrystal. The vortex phase seems to be appearing again, and the supercrystal seems to be appearing to be forming, and the supercrystal is actually absorbing this vortex. As you might remember, the supercrystal is really some sort of DNA origami of the vortices itself. So these vortices are now part of this supercrystal. And those original ferroelectric domains, they don't recover. They're gone. Okay? So there's all this dynamic going on, that there is a collapse, and then what I call the primordial soup. There's this thing that is very hot. It's a hot soup. I'll show you it's on the order of 600 Kelvin or above. And then it's cooling and cooling. The soup is cooling. It's like crystallization. You need to cool the liquid. It's nice and super saturated. And then at some point, this supercrystal phase will start forming on the order of 10 nanoseconds or so. Okay. All right. So this is where the supercrystal starts forming. You can see initially there's the vortex, before, and the supercrystal is not really there. This is some disordered phase. At 100 picosecond, you begin, so this is highly dimmed, and the vortex is, not completely gone. It is there. I should be clear. This is not zero, right? So this is a little bit. So a little bit of this vortex phase keeps hanging around, and the ferroelectric part is also, looks like it is hanging around. There's a very, very little bit of this. And you'll see that the ferroelectric never really recovers. It's the vortex that recovers. Okay. And after 500 nanosecond, you can see the supercrystal phases forming. This is the first order, second order, third order peaks. So if you take a cut here, that's the cut here. This is the first order peak. Right here, you zap it, and nothing happens all this time. Around 10 nanosecond, the supercrystal first order is coming, third order is coming up. It's very important to have these higher order to be sure that you have the supercrystal phase and not some other regular phases. And so, this phase is arriving, and then, it fully forms over hundreds of nanoseconds. So a lot of things happen here. So just to summarize in a simple chart, within a picosecond, the initial vortex and ferroelectric twin phases, they collapse. Okay. And there is something called it, what is remaining there. I said a little bit of something is remaining. It's really not vortex or this ferroelectric phase. It is transient C plus C minus phase. In other words, it's very weak ferroelectricity. It's very hot. And so it's up and down, up and down. So there's a little bit of polarization, up and down polarization that's hanging around. About 1 to 20 picosecond, it's thermalizing, there's some acoustic, and there's all this primordial soup, right? You're starting to approach 10 nanosecond, the vortex is starting to reemerge, then the supercrystal starts reemerging along with the vortex, and they keep growing, and then beyond this, the supercrystal slows down, but it's fully growing into a complete phase. Okay, so that's a lot of information. Let me take a second attempt at a better cow, not a square cow, but something that, with Long King Chen's group, with a lot of these experiments also motivate new, theoretical and numerical tools, right? So phase field modeling is a quasi-static simulation where you're doing time-dependent, variational minimization of the Landau-Ginzburg energy. You wanted some dynamic component to it, where you can look at femtosecond, picosecond timescales. And in addition, this particular experiment has a lot of other things going on. You have carrier dynamics, you need to incorporate that. Polarization dynamics, which is Klein-Gordon equation, and that's the basis for this dynamical phase field modeling. Here is an original paper we published where in barium titanate we saw pump probe experiments with some strain dynamics that were simulated by this DPFM, dynamical phase field modeling. It's all based on this Klein-Gordon equation, elastodynamics, temperature evolution, electrostatics. So you have to put all of these in. Now we are starting to think about microscopics and build a code and then compare with whatever the X-ray and all the synchrotron studies are telling us. And here are very preliminary results. These are, you have to take some of this with a pinch of salt because we are still working on it, like I said. Some of this initial rise times are not matched with experiments, yet we still need to work on it. But you can see temperature evolution, carrier evolution, and average polarization evolution. So the takeaway from this is very quickly with that punch, within a few picoseconds, but here in this simulation right now, it's showing nanosecond, you get very hot. It's 600 Kelvin. Okay, and it's slowly cooling, and this cooling is that primordial soup. Okay, so you start with some mixed phase here, and then you're cooling this. This is, and as I said, it's some kind of very weak vortex. It's really some sort of C plus C minus domain, up and down, up and down. And remember, that is now possible because we are flooding these interfaces with charges. So earlier, that divergence of polarization was preventing the polarization from running into the interface. Now, because it's flooded with charges, it can stand up and not have to coil up and make swirlies. And that starts happening as soon as you pump this with charges. And then that is cooling, and starts the supercrystal starts nucleating eventually over 50 nanoseconds and beyond. The supercrystal phase is starting to form. So the carriers, you're pumping quite a bit, 10 to the 21 carriers per centimeter cube or 10 to the 27 per meter cube. And the polarization, you can see that immediately there is a collapse. There is this primordial soup I was mentioning right here. And then slowly the vortex part and the supercrystal part, they are evolving. They're coming back out. On tens of nanosecond timescales. So these are initial simulations. These things are going to get better. We are looking at things more microscopically. Here are a lot of the details. We have to stare at them a lot more, but I can already give you some smells of it. So here is that vortex phase that's really that primordial soup phase. The polarization is trying to, mostly up and down. The electron concentration and hole concentrations, initially it's all flooded and uniform. You can see now it's starting to segregate. Electrons and holes are starting to segregate because all this polarization, as it develops, as it cools down, the polarization goes up. See, getting darker in color. And that is going to start locking up some of these charges we have pumped. And so you can see the charges are moving around. They're getting locked up into that charge ordered state. And over the supercrystal phase, they have segregated. It continues for hundreds of nanoseconds until the full supercrystal is formed. Okay. Now, some of the questions we are addressing, we're thinking about it. It's still early stage. Is can just carriers do it? And the answer is no. We don't get the supercrystal phase. Can you just heat it and do it? And it turns out no. It just leads to some ferroelectric phases. You really seem to need carriers and charge. So it really needs a jolt of charge and heat. It needs a double punch. Within that electron phonon thermalization timescale, within that 1 to 10 picosecond, if you spread it out longer than that, the punch is just not enough. So you need to do that, and you get if you have both of them, you get this supercrystal phase. So let me summarize. I'm getting towards the end of the talk. I have a few more slides to wrap up the story. Is that this really the saga of supercrystal formation is coupled dynamics of charge, strain, and temperature. You have starting phases, you're nuking them with a real punch of charge and heat. And then there is this primordial soup, as I call it. It's just cooling and cooling. And eventually this amazing crystal with tens of nanometer crystal unit cell emerges. There's a lot of basic questions. Do we need the sort of competing phases to generate something new? Does the topology of these phases matter? All the defects and how they wind and unwind to form new structures. What is so special about this soup? It's some amazing things are emerging from it. But what is so special? Can I get it any other way than by light? And can I do some other tricks? This is one beautiful serendipitous discovery. We are beginning to understand why, but can we make this more predictable? Can we generate many more metastable phases? And can we track these transition pathways? And some of the theory tools that I described, especially dynamical phase field, is going to be very useful there in tracking transition pathways. Okay, I'm going to switch track for 2 slides to tell you about vortex dynamics and skyrmion dynamics. Again, stuff that is, some of it is cooking. And as I said in my abstract, I won't have very much time to talk about them, but only a few slides. And I'll conclude.
Yeah, Venkat, we're like 10 minutes into our discussion time.
Oh, okay. So maybe I should skip this. Yeah, okay. Thank you. Thank you for mentioning that. So maybe I'll come to my final slide here, which is, how do you train your supertexture? You have to have competing phases. You have to trigger the system, and you have to map the system using real-time techniques, and you need tools to go at it. So sorry about that. I didn't see your chat discussion, but let me stop here, and I'm happy to take questions.
Yeah, that was fantastic. That was great. Really appreciate it. I think everybody does. So really exciting. Let me see. I've got a question here. Marius Hundemichael asks, thank you for a very interesting talk. I might have missed it, but could you explain the primordial soup? Is it a temporary ferroelectric phase, or is it a collection of polarizations in random directions?
Yeah, so let me go there. So the primordial phase is, this is still 600K. The ferroelectric transition for lead titanate is more like 450C, which is over 700 Kelvin. So it's still polarization, but the polarization is much weaker, and it is more or less, you can look at some of these vectors here. They are really sort of up, down, up here and down here, and up here and down here. So currently we are tentatively calling it C plus, C minus. It's really up and down, but very weak. Polarization is very weak. So that's currently what we think that primordial soup is.
Okay, great. I have a quick question, and then there's another question I typed in. So I'm wondering about what kind of like bulk properties are like when you have the supercrystal, like susceptibility or piezoelectric response. Is it very different than it would be in the ferroelectric phase?
That's a good question. we haven't found a real good use for it. For the dielectric constant of this thing, I think I'll have to ask Vlad. There was nothing remarkable. We were expecting maybe that this thing is going to have very high dielectric constant. It does trap a lot of charges, but on tens of nanometer scale, it's holding a lot of charge, but it's not like a very strong tunable dielectric. I mean, it locks in, and it's locked in pretty well. Piezoelectric, again, because it's got all these twists and turns, the net piezoelectric coefficient is not very large, right? So unless you pole this thing in some direction. So at this point, we don't have like a killer application for, hey, this is what this is good for. But if Vlad is online, maybe he can. Vlad, I see you. So do you have any comments? You made some of these measurements.
Yes, I was watching actually the live questions and try to answer that. So what was the question here?
Were there interesting dielectric constant or piezoelectric properties of these?
We have tried to use PFM and observe that. And our reported paper, we have some images of this supercrystal periodicity along this direction, where we have modulation of in-plane, out-of-plane polarization, vortex in-plane. So then, that suggests it has a piezoelectric activity indeed at this 30 nanometer. We haven't measured the coefficient, but the observation in PFM supports that. Dielectric constant, we haven't observed a difference compared to pristine, compared estimations in Raman spectroscopy. Direct dielectric measurement, electric was not done yet.
Okay, we're really running out of time. We've got a bunch of questions typed in. Sean, is there a way to save these questions and have them answered afterwards by email?
Yeah, we'll get a list of all of the questions, but I don't know how you would reach out to people without their email address.
Oh, well, maybe in the question thing, put your email address if you'd like an answer, because we're really out of time. I want to thank our speaker again. I'm going to have to wrap things up because I have a couple announcements to make, and we've only got like 1 minute left. So thank you so much, Venkat, for a fantastic talk. I'm going to go ahead and share my screen again, if I can. That was great, and I think everybody learned a lot. I just want to say that we're continuing to have these lectures. The next one will be December 16th by Sergei Prosendiv. Hidden phases with neuromorphic responses and highly enhanced piezoelectricity and relaxer and anti-ferroelectric prototypes. So please join us for that. And I should say again, we're going to try to answer everybody's question offline that you typed in the typing thing. I wanted to make sure that I mentioned the registration site will go live very soon. So please be on the lookout for the registration for the Ferro 2022 Ferroelectrics workshop, Fundamental Physics of Ferroelectrics and Related Materials. So it will be in Washington, D.C. At the Carnegie Institution on Bread Branch Road Northwest, and we'll be using a hotel in Chevy Chase, and it will also be available virtually. And the only downside is we've got a limit of like 60 people on the on-site venue. Is just COVID restrictions. So please register early if you'd like to come. And because of this, people that come to the meeting should be people that are planning to make presentations. If you want to just observe, then you should do the virtual option. Okay, well, thank you all, and hope to see you next month. And thanks to the speaker again. Professor Gopalan gave a very exciting and interesting talk, and I hope everybody got a lot out of it. So thank you
very much, Ron.
Thank you.
Appreciate the opportunity.
Thank you. Bye-bye.